Progress is impossible without change, and those who cannot change their minds cannot change anything.
Hi all, Dr. Clark here. And for this lecture, we're going to talk about natural resource cycles. Okay? And that process of cycling different elements or process of cycling different molecules is very important to environmental science. Environmental science examining the ecosystems on the planet, they just wouldn't be the same if you weren't also examining the cycles and how resources are cycled through different systems. Okay, we're going to talk about quite a few cycles, and we're just going to briefly touch on them. We're not going to dive really deep into them, but I just want you to realize that things aren't stagnant. Okay? Things move from one system to another. Things change form. We've talked about this when we were talking about energy. Remember, energy is not created nor destroyed. It just changes form. Well, these resources are the same. These resources are just changing form. Okay? So we're going to talk about things like carbon dioxide cycle or the carbon cycle. We're going to talk about water cycles. Okay, these two are probably at least as introductory to environmental science, these two are the most important cycles that you can understand. The other cycles that we're going to examine, phosphorus and nitrogen, these cycles are a little more specialized. They're a little less abundant in the sense of the material is not readily used every single day by everyone. But we're going to look at their role also as we progress through the cycles. So cycles of matter, that's what we're talking about now. This matter can occur in a couple different forms. Remember, matter is just a measurement of something that takes up space and has a mass. Now, the water cycle is a cycle where we're discussing a molecule of water, H2O. Right? Now, that water cycle is going to have different forms. We might have solid H2O, liquid H2O, vapor H2O, but we're talking about H2O. On the other cycles, we're going to be talking about matter that is comprised of certain elements like carbon, nitrogen, phosphorus. Now, the important thing that we've discussed before and we'll discuss many, many more times is that the Earth is a closed system. Now, yes, photons come to the planet and heat leaves the planet. But in regards to water, nitrogen, phosphorus, carbon, these other elements, it's closed. No new elements are coming in, no elements are leaving. So very little ever enters our planet except for this free energy we get from the sun, and very little ever leaves our planet except for things that we might, take out into outer space stations, satellites, these kind of things. And then, of course, heat, that excess energy from the sun that escapes out of the planet, which is a really good thing. Otherwise, we'd be cooking each other. All right, so when we look at the biogeochemical cycles or the biocycles, it's important to think about this as recycling. Because nothing new is coming into the system, the material that is left over after we use it or after it has had a given purpose is recycled and placed back into the system. This is why it's very important to realize that just taking garbage and taking material and dumping it into a landfill, you're eventually going to recycle that material anyways. Now, maybe it will be hundreds of thousands of years when that material has recycled on its own, but no new materials coming in. So if you're going to dump iron and steel into a landfill, you're just going to have to dig up that ore from some other part of the planet. So you can see that you're just moving the problem from one area to another. If you could recycle this material, then you don't have to dig up that material as often. You also wouldn't have to place it underground or wherever you're going to put your waste material and allow for it to decompose over a long period of time. You can start that decomposition or recycling much faster. We'll get into recycling and the ways at which we recycle things like plastics or fossil fuels and other things like tin and aluminum and these kind of things, and what that process looks like and where's the pitfalls. Guys, some of the pitfalls really have to do with our technology. In some cases, we might not be advanced enough to recycle that material efficiently. And we'll examine this in future lectures. But right now we're going to talk more about the cycles that really, yes, humans play a part, but these cycles would occur without the presence of humans and do occur without the presence of humans. And that'd be cycles like water, carbon, oxygen, sulfur, nitrogen, phosphorus, and there's quite a few others that do cycle through the system. The water cycle, like I said before, is probably the most important cycle. Again, when we're looking for life on other planets or in other regions, it's revolving around water. As we know it, life cannot exist without water. Well, water has very unique properties. Probably the most unique property is that solid water, i.e. ice, is less dense than liquid water. This allows for ice to form and float on the surface of liquid water. Without that capability, there wouldn't be life on this planet. Okay? There wouldn't be life on any planet if water was more dense as a solid form. So it's that one main unique variable that ice floats that really gives us the ability to have life on this planet. Another unique piece is that water evaporates. Right? And that evaporation process, whether that's evaporation from the ocean, the lakes, the streams, even evaporation off of glaciers, etc., whether that's evaporation or transpiration, which is basically water loss from plants or respiration from plants. So plants have little teeny pores on the bottom of their leaves, which we call stomata. And when they open those pores to take in carbon dioxide, they release water. In some cases, it's, I don't want to say on purpose, but in some cases, they release excess water. In other cases, it's water is escaping the tissue. But at any rate, both evaporation and transpiration eventually becomes condensation. Okay, so it condenses. And this is due to a process called cohesion. Cohesion is the attraction of water molecules to other water molecules. And so due to that cohesion, you have condensation. Condensation then accumulates enough that those water droplets or water condensation is heavy enough that it can form precipitation. Precipitation can then come in the form of snow, rain, sleet, other ice forms, whatever you want to call them, hail. There's lots of different words for different types of precipitation, but it comes in form of precipitation. That precipitation eventually makes it into a form of runoff. That runoff could be in the form of lakes, streams, rivers, whatever it might be, making its way back to the ocean, making its way back into plants, making its way back into evaporation, into condensation, okay? Or it can go into the groundwater and then be stored in the groundwater for some time until that groundwater is either utilized, which it almost always is, or something occurs to where the groundwater can escape, penetrate another river. You might get springs or something like that where the groundwater is coming up to the surface and then can start this transpiration, evaporation process all over again. Okay. We'll approach the water cycle again. Like I said, it's really important for environmental science. It's a cycle that we know a lot about, but it's also a cycle that we need to make major changes with. Not changing the cycle, but changing our footprint or our role in disturbing the cycle. Okay, which kind of brings me to this, and some of you might have heard this before, or some of you may have even watched the film The Big Thirst. But this is a quote from The Big Thirst that I'll read real quick. So all the water on earth, the water in your Evian bottle, the water in your glass of water, the water you use to boil a pot of spaghetti, all that water is 4.4 billion years old. In other words, all that water is the age of the earth. So when the earth got established, at that point, water became established on the earth, and all of it, every bit, still remains today. There's no water molecules being added, and there's no water molecules leaving. All the water we've got right now has been used over and over again through that cycle that I just went through, along with other organisms contributing to that cycle, like sweat, urine, spit, anything that has the capability of having water associated with it is part of that water cycle. Again, those water molecules don't go anywhere. They're captured on this planet. They just change form. Okay, so liquid water eventually becomes vaporized water, eventually becomes solid water, back to liquid water, etc. Okay, now for some of you who like to think of things a little bit differently, every drink of water you take, every pot of coffee you make is dinosaur pee, okay, or dinosaur urine. Or you pick another animal that's been on the planet for a long time, whales or dolphins or fish. It doesn't really matter. All of the drinking water that you consume has once ran through the kidney of multiple organisms: dinosaurs, lizards, birds, mammals, fish. It's been through their kidney. So because it's all been through the kidneys of Tyrannosaurus rex or T-Rex or any Apatosaurus many, many times, because all water we have is all the water we've ever had. Which makes, this quote makes for things like, I'm not picking on this brand. I'm sure it's perfectly fine water, but it makes for things like water companies to have ironic slogans or ironic ideas. Okay, the Atlantic rain, or this water that's sold, captured directly from the sky in the west of Ireland after its journey across the Atlantic Ocean. Unique source, unique taste, unique story. The only thing that's probably unique is the story. The source, it's the source of all water. The taste, it's highly unlikely, unless they're altering the taste, it's highly unlikely that if it's directly from the sky, that the taste is anything unique. The story is, if you're talking about the story of this company, of course that's unique. So I just want you guys to think about water from that standpoint. If you go and you buy a bottle of water, maybe you're buying that bottle of water because you believe that this company is better for the environment. Maybe they use 100% renewable or 100% recyclable material, or maybe through their processes they're less wasteful, etc. Maybe you're buying the water because it has this unique branding that people who buy this water are, rich or drink a more high quality water. Water is water. Yes, it's true that you could have different minerals in this that make the water taste different. And that is quite possible. So the taste could be different, but it's not due to the water. It's due to the minerals that might be present in that water, or that are present in that water. All right, let's look at the carbon cycle. Carbon cycle is obviously big news today. With global climate change, a lot of the climate's temperature increase is associated with increases in carbon dioxide in the atmosphere. As you increase carbon dioxide, you decrease how much energy, how much thermal energy can leave the atmosphere. So carbon dioxide levels, if they're high, they capture heat and keep that heat in the region for a longer period of time. It doesn't allow for that heat to dissipate out. That's one of the issues. We'll talk a lot more about climate change and the role that it plays and the science behind it. But right now we're going to talk about the carbon cycle. And like I was saying before, carbon cycle is a little bit different than the water cycle, because in the water cycle, we're talking about different phases of water. So we're talking about liquid, vapor, solid. In the carbon cycle, we can be talking about different phases of carbon, but we're also talking about different molecules. So we can talk about gas, of carbon dioxide. We can talk about material that makes up trees, cellulose, different types of carbohydrates like glucose and fructose and sucrose. We can talk about products that are coming from fossil fuels. So ancient products like coal and natural gas, oil, they're all going to have a different chemical composition. In some cases, it's a, simplistic chemical composition in the case of carbon dioxide. In other cases, these are really big molecules with lots of other things attached to it. All right? And so breaking up large molecules like coal or large molecules of carbon, in the form of natural gas, etc., can cause other chemicals besides carbon dioxide to be released. Burning of trees can have other things other than carbon dioxide being released, right? And you can have other material. So when we talk about the carbon cycle, a lot of times it is associated with other materials. So maybe sulfur is associated with it. Maybe nitrogen is associated with it. It depends on where you're talking about in the carbon cycle. But overarching, when we talk about the carbon cycle, we can talk about the role that plants play in capturing carbon. So we've talked about this before. We talked about it with photosynthesis. Carbon dioxide is consumed by plants. Right? That carbon dioxide is consumed by plants. It is then converted into chemical energy, stored energy in the form of starches, glucose, fructose, sucrose, cellulose. These are carbohydrates. So that carbon gets bound up into carbohydrates. That carbon dioxide can also be bound up into marine or aquatic systems. It could be bound up into aquatic plants. Okay? So if you're looking at things that occur in shallow regions like coral reefs and aquatic plants, they're doing photosynthesis. They're taking in carbon dioxide and storing it. It can be bound up in the sediment of the oceans and rivers and streams and lakes. It can also be dissolved into the water and be utilized by other organisms in the creation of shells and other things. So you can have calcium carbonates and other substances forming from that capturing of carbon dioxide or carbon molecules that might be in the rivers that you're getting on the runoff, etc. Okay? So you have this big cycle, not even talking about the role that animals play. Animals, their cellular respiration, the waste product of that is carbon dioxide. So all animals are expelling carbon dioxide, right? And those plants, in a perfect system, there's enough plants on the planet to capture that respiration from animals and reutilize it to form carbohydrates. Man plays a role in this, obviously. Man is digging up ancient carbon storage, okay, in the form of things like oil, natural gas, coal, okay, even other products that you might be utilizing to make building material. Some of this is carbon-based, and we're digging it out of the ground. These are ancient storage deposits, okay, from plants that have been buried and animals that have been buried under high pressure. That's how you get coal and oil and natural gas. And, we're digging it up and we're utilizing it. And so it shouldn't be a surprise that if you're digging these ancient stored carbon deposits up and you're burning it off, that you're increasing the amount of carbon that is in this cycle faster than that carbon can be deposited back into the storage. So if it takes 300 million years for plants that have been buried in the soil to be converted into coal or oil, Well, we haven't been around for 300 million years and we're burning that coal and oil. So it's going to take a very long time before those soils can capture that material again and convert it back into stored carbon. Again, we'll come back and look at this cycle at a later date. Nitrogen. The nitrogen cycle, like we stated before, most of the air, most of what makes up what we call air is nitrogen gas. Nitrogen gas, we get, things like nitrogen fixation that can come from lightning. We can get nitrogen fixation that comes from bacteria, that comes from fungi, that comes from the association of different things with plants. And that fixation is important because, like the carbon cycle, we're talking about gases that can then become fixed and utilized by other organisms. Not in the form of gases, but in the form of things like nitrates and nitrites. Okay? And so these are nitrogen-based material that can be utilized by plants, and then those plants can be consumed by animals, and that nitrogen is important for that process. In fact, a lot of proteins have a nitrogen component to them. And so you get peptide bonds which are forming between carbon and nitrogen, and that nitrogen has to come from the nitrogen cycle. It's returned to the cycle through defecation, and then the consumption of that material and the fixation of that material again. So you have lots of ways at which nitrogen can be fixed. Lots of different organisms can fix it. You have bacteria and fungi that can do this. You have some plants that can do it on their own. But at any rate, they're fixing nitrogen into a usable nitrogen form. Okay. Now, we can talk about what role humans might play in this cycle. We know that one of the three components needed for plant growth is nitrogen. And the majority of our fertilizers are heavy in nitrogen. So we can remove nitrogen from deposits in the soil, and utilize those nitrogens to grow food crops faster and more readily, etc. In doing so, we interrupt the nitrogen cycle. We might overload the nitrogen cycle in one system. We'll talk about some of the problems with that overloading a system with nitrogen or phosphorus or even carbon. If you disrupt this cycle too much, you can see that you'll have problems, or you can see kind of a pitfall that comes out of that cycle. We'll come back a little bit to the nitrogen cycle. Phosphorus cycle, much like the nitrogen cycle, we know that phosphates or phosphorus is important for plants. It's one of those three components that plants really need. They need nitrogen, phosphorus, and potassium. Nitrogen is normally used for heavy tissue growth. So nitrogen is directly associated with growth of typically green material. Phosphorus and phosphates are important for flower production and fruiting production, right? Or more important for flower and fruiting production. So you get those three kind of components to those three components are what fertilizers are typically made of. With some other things, sometimes calcium and some other things that maybe certain plants need. But those three are the big three that majority of our fertilizers are utilizing. So how do humans get into this system? Well, we might extract phosphates through mining operations and deposit them as fertilizers on fields, etc. Okay? So we're adding another loop to the system. Under normal system, you might get that phosphates or phosphorus coming from the erosion of rocks, coming from the decomposition of organisms, rotting organisms. That gets back into the soil. Maybe it gets dissolved into the water. It's uptake by the plants through the water system. Sometimes it's deposited directly and you get decomposition by the plants that are growing on that material where the rock is eroding or where the organisms are decomposing. Okay, so that humans throw their own little loop in. Okay? They cut out the middleman. They cut out that erosion of the rock. They cut out that decomposition of dying organisms, and they dump excess phosphates onto fields, onto cropland. This can cause problems if that phosphate and phosphorus gets back into the water system, which it often does. Can cause huge plant growth that occurs inside the water system, so you can get algae blooms and other things. We'll come back and talk about the causes of some of the disruptions. But remember, we're just talking about the cycles. Okay? And like the nitrogen cycle, like the carbon cycle, these phosphates are taken up in different ways. They can be stored for a very long time in marine sediment. And they can be stored for a very long time in rocks or in, material that is buried under the ground. And that release can be very slow over time. Again, we'll come back. So those are a few of the cycles, some of the biggies. But I want you to think about what do all these cycles have in common? What is the common denominators that all cycles have? And the first thing that you should think about, or hopefully that you're thinking about, is this connection between water and land. All the cycles, regardless of whether we're talking about the water cycle, obviously there's a connection between water and land there. But if we're talking about the carbon cycle, there's that connection between, depositing carbon on the landscape, either in the form of trees or the form of old trees turning into coal and oil and natural gas. And then that role that the oceans and the aquatic systems play in capturing carbon either from carbon dioxide or capturing it in aquatic plant forms, etc., and holding on to it for a long period of time as a storage device. That's kind of how our oceans work for carbon, is they become a storage device. Same thing with nitrogen, phosphorus, etc. The other thing is you should be examining or thinking about, okay, well, if there's a connection between water and land, is there a connection between fresh water and ocean water or salt water? Is there a connection between marine environments and freshwater environments? What's the role that these different systems play? Are the freshwater systems, are they also a deposit for some of these cycles, or are the freshwater systems just moving the material to marine systems? And then the final one that I want you to think about is the human effect. And we're going to come back and examine this in much greater detail. But what role do humans play? It's not all bad. A lot of, the cycle disruptions are negative because humans have found out a way to speed up the cycle or to divert the cycle for human needs. Okay, but what are some of the other ways at which humans, the other roles at which humans have in these cycles? That's also important to see, and we'll come back and discuss some of those disruptions and also some of the ways at which we are trying to change that disruption or trying to, remedy the cycle so the cycle moves as smoothly as possible with humans in the ecosystem. So those human effects, again, they can be digging mines and mining off phosphates, mining off nitrates, pulling carbon out of the ground, etc. There's lots of ways at which this, pouring it onto fields and having leaching occur, dumping, the waste material into the waterways. There are all kinds of ways that humans can affect these systems, and we'll come back and examine these. Okay. So, jumping back and connecting it all together as much as we can at kind of a general baseline system, we talked about what plants are made of. Beginning of the entire lecture on energy and matter, we talked about this whole idea that plants are getting their mass, they're getting their material from the soil. Well, we know that from experiments like Jean-Baptiste's experiment that this is not true, that the majority of the mass is coming from material in the atmosphere. That being said, we also know that the soil plays an important role. Okay, yes, plants are made of carbon-based material. Okay, the source of that carbon-based material is carbon dioxide, for the most part. Okay? That carbon-based material is making up the tissue of the plants, the energy storage of the plants. Okay? That's all carbon-based. Another piece of that is oxygen. Okay? Oxygen from that carbon dioxide. So, when we look at plants, they're about 45% carbon, 42% oxygen. About 6.5% hydrogen. This is coming from water. Some of this oxygen is also coming from the water that is utilized from the soil. Nitrogen, that's coming from the soil, and other minerals like potassium, phosphorus, sulfur, even some carbon that's coming from the soil. Okay? But it's important to know that, yes, even though, maybe only 6, 7, maximum kind of a 10% of the mass of a plant is coming from the soil, that 10% is also very important. Plants can't just survive on carbon alone. Okay? They need nitrogen, they need potassium, phosphorus, they need some of these other trace elements in order to construct DNA, in order to make bonds between carbohydrates, make bonds between proteins or amino acids. Okay? And so that role that some of these other elements and some of these other pieces play can be large. But the overarching answer to the question, what are plants made of? They're made of carbon. Even though often this is not realized by very many people. Okay? but carbon is what makes up plants. And so that's important because when we talk about carbon dioxide, when we talk about that carbon cycle, plants are a huge component of that carbon cycle. You remove the plants, you remove a massive amount of carbon sink. And you start releasing that carbon back into the atmosphere, and then you can have problems. You plant more plants, it's possible that you have less carbon in the atmosphere because these plants are consuming that carbon and utilizing it to build tissues and sugars, etc. So again, this role that plants play, this role that animals play, it all has to do with giant cycles. Okay? And these cycles can be disrupted by fire. These cycles can be disrupted by floods. These cycles can be disrupted by humans cutting down forests or killing animals, whatever it might be. The cycle can be disrupted. But eventually, it doesn't matter how you disrupt the cycle, eventually the elements will return to the soil. They will be reabsorbed and they will continue the cycle. We know this even if we're binding up these materials in things like houses, in things like, large buildings, in big cities. That when everything is said and done, and the people are gone, and the city is gone, over a long period of time, all that material will return back to the soil, and plants will come back on the landscape and utilize that material again. Now, sadly, it might be without humans that this has to happen, but it will happen. Just like a forest fire, a fire that runs through, burns up all the material. Eventually, the trees will come back. Eventually, the vegetation will come back. Now, for forest fires, we might be able to see that in our lifetime. For cities, for apartment buildings, for skyscrapers, for cement pads, whatever it might be. We might not be able to see that in our lifetime, but eventually the vegetation will come back. Okay, so with that, we're going to talk about ecology and evolution next time.